In this tutorial of AquaCrop, we will discuss some ideas related to irrigation uniformity. The idea is that the variability of irrigation applied in the field has an effect on the relationship between yield and water applied. The actual amount of irrigation received in the different points of a field is never exactly the same. The variability of irrigation is characterized with the uniformity coefficient. The classical uniformity coefficient that has been used is the one of Christiansen, which is equal to 1 minus the ratio of the sum of the deviations of the amount of water applied as compared to the mean divided by the sum of the values of water applied. More recently, the more commonly used is the uniformity coefficient of the low quarter, also called distribution uniformity low quarter, which is the ratio of the mean depth in the areas of the field that correspond to 25% of the field receiving less water divided by the mean depth. This is an example of a distribution of applied water in the field. So in the x-axis we plot the fraction of the field, that means fraction area of the field, and in the y-axis we plot the applied depth. We see here in the blue line that the applied depth is as low as around 50 millimeters, and it increases in the different places up to 130 millimeters. This horizontal line is the target depth, which means the amount of water that we require to apply. This is the average applied depth, 98. And this red line is the mean depth of the low quarter. For this case, the distribution uniformity of the low quarter is 74. We see here a lot of variability in the amount of water applied in the field, and this can happen commonly. If the distribution of applied water follows a rectangular, in other words, uniform distribution, which is the simplest distribution that we can use, then the distribution uniformity of the low quarter is equal to 1.5 times the uniformity coefficient of Christiansen minus 0.5. So both uniformity coefficients are related. Here we see examples of uniform distributions of applied water. In this case, if we plot the amount of water applied, 1 would correspond to full irrigation, which means applying the evapotranspiration of the crop. We see here that with this uniform distribution, which means that the applied water versus fraction of irrigated area is a linear relationship, as we see here, we see places in the field where the amount of water applied is less than that corresponding to full irrigation. In other words, in this area of the field, we are irrigating less than required, so we have a deficit area. On the other hand, there are other places in the field, here, where the amount of water applied exceeds the one required for full irrigation. In other words, this area of the field is over-irrigated. We plot here another situation where we are applying this mean depth, the discontinuous line, and we see that in all the locations of the field, the amount, the depth of water applied is less than that required for full ET. This means that we are in a situation where in all the field we are suffering water stress. It's a situation of deficit irrigation. To illustrate these ideas, we will go back to the same case study that we had on a previous tutorial, where we grow a sorghum crop in Hinojosa, Spain, in the year 2012, being planted on April the 1st on a sandy loam of 1 meter with a restrictive layer at 0.6 meter depth. The criteria for irrigation scheduling is irrigate whenever 100% of the readily available water is used, and then apply an amount to bring back the soil to fill capacity. The readily available water is around 59 millimeters. With those criteria, if we use AquaCrop, we determine that 5 irrigations, each of 61 millimeters, this is roughly equal to the readily available water, are needed. Note that these 5 irrigations have been calculated after discounting the last irrigation that was explained on a previous tutorial. Now the question is, what happens if we apply those amounts and we are irrigating with sprinklers with a uniformity coefficient of Christiansen of 0.75? A uniformity coefficient of Christiansen of 0.75 means that the extreme amounts supplied in the field for each irrigation are minimum value, which is calculated using this equation, mean depth multiplied by 2 multiplied by uniformity coefficient minus 1, and the maximum value is multiplied by this 3 minus 2 by the uniformity coefficient. The results are 30.5 for the minimum amount in the field and 91.5 for the maximum amount applied. It is clear that there are places in the field receiving too much water, while other places receive too little. To determine the consequences, we will use AquaCrop with the option of irrigation schedules, which means that dates and amounts of irrigation are inputs. The extreme values of irrigation amounts, as you recall, are 30.5 and 91.5. Now, we divide the field in 5 zones, each representing 20% of the field area. The midpoints of the 5 zones will receive irrigation amounts of 36.6, 48.8, 61, 73.2, or 85.4. Note that 61 millimeters, the average amount, is located in the middle of this list. Well, because it corresponds to 50%. This is the class that goes from 40 to 60%. The other values are obtained by interpolation between 30.5 for 0 and 91.5 for 1, taking the values of 0.1, 0.3, 0.5, 0.7, and 0.9. Now we go to AquaCrop and simulate yield for the 5 zones with irrigation amounts of 36.6, 48.8, 61, 73, and 85.4 respectively. Now we will calculate the different simulations for the different areas of the field using AquaCrop. We enter AquaCrop and choose the climatic file for Hinojosa, including 2012. We go and select the crop, which was sorghum STD for sorghum standard, and it is planted on the first day of April. Then we get the soil profile, which is SL100 res, which has a restricted layer at 0.6 meters. Now for irrigation, we have 2 possibilities, or 3 possibilities. we can input dates and amounts of irrigation, this irrigation schedule option, or we can let the program generate the irrigation schedule. Let's do that first. We create an irrigation file. For instance, we will call it sample. Description, whatever we want, sample, for instance. This is a sprinkler irrigation, and we have 100% of wetted soil. In the next part, we find the time and depth criteria. We're gonna irrigate with a timing according to the readily available water. When will we irrigate? When 100% of the readily available water is depleted. And then we will go back to fill capacity for depth criteria. This is the most simple strategy for irrigation scheduling. In this same page, we could also change the quality of the water, of the irrigation water. In this case, we're gonna assume that the irrigation water is excellent. We click on create, and then we're ready to go and run the program. The AquaCrop will calculate the dates and amounts of irrigation according to this criteria. We click on start, and we see here the water balance. These are irrigations, 1, 2, 3, 4, 5, 6 irrigations. If you remember, in our last tutorial we discussed that we don't want much water to be left on the soil at the end of the growing season. Therefore, we already deduced that the last irrigation could be omitted. Therefore, we would only have 5 irrigations. Going to numerical output, we can see the soil water balance, and we can move down to see what is the amounts and dates of irrigation. We scroll down and we will find that the first irrigation, 60.3 millimeters, is applied on the 23rd of May. If we go down, we will see that the next is June the 1st, and then June the 13th, and then June the 23rd, and then July the 3rd, and we would have this final irrigation on July the 16th that we have already discussed that should be omitted. For simplicity, we're gonna assume that all irrigations have a mean net application of 61 millimeters. Okay? Now we go back to the main menu. We don't save the we could save the output files. We can name that as, for instance, sample, assign to the output files, and then we will able to tell which are the files related to this last simulation. Click on OK, and all the files have been created. Why do we do that? Well, if we want to write down or extract the dates and amounts of irrigation. Okay, once we know the dates and amounts of irrigation, we go back to the irrigation and select create irrigation. Now we are not using this generation of irrigation schedule, but we will input the irrigation schedule. We click on create irrigation file, and we will call it sample 2. And the description is input irrigation schedule. And then we have irrigation method, sprinkler 100%, wetted area, and irrigation events. In this page we can put the dates and amounts of irrigation. For instance, we could put an irrigation on day 53 and the net application, as we said, of 61. And then we can put all the other irrigations up to 5, and we are assigning a water quality of no salts at all, which is easy equal 0. Click on create. It's okay because we have already input S1, it is called X160, this one. Display. These are the same dates that the program calculated for us, but now we have input them into the program with a net application. This should be the minimum amount of water that should be applied to that field to get maximum yield. Okay, now we go and run the model. Look at this. We are getting the maximum yield, which is around 9 tons per hectare, and we are leaving the soil almost empty at the end of the growing season. So, in principle, this schedule would meet the irrigation requirements of the crop. As we said, if we apply on an average 61 on every irrigation, there are places in the field that will only receive around 30 and places in the field receiving around 90. This is due to the uniformity of the irrigation system. So, going to the main menu, here we would save, for instance, sample, call it sample level 50, assign, and then click OK, so we can later review the results of the simulation. So we go by one changing this irrigation schedule for sorghum from 30 millimeters per irrigation up to 90 millimeters per irrigation, and we save all the results. Here we can see the results of the simulation using AquaCrop for the 5 zones in our field, going from the level 20 to 100. These are the 5 areas that we have divided at our field. So this is the total irrigation applied. If we apply 31 millimeters per irrigation, we have a total of 185, and the mean value of irrigation applied to the field is 305. Okay, according to AquaCrop, if we apply only a total irrigation of 185, we will reduce yield and get only 4.6 as compared to 9 when we apply full irrigation. Here we see that in the 5 areas of the field we are getting, in 3 of them we are getting maximum yield, but in 2 of them we have reduced yields. Why? Because we are getting not enough water for maximum evapotranspiration and maximum yield. The average yield in the whole field would be 7.8. It means that we are losing around more than 1 ton per hectare because of applying just the average, the amount of water required for the average evapotranspiration. We could also, or in principle, we could apply more water. The optimum amount of water that we need to apply for a given field with a given irrigation uniformity is given by this equation. In this equation, Qi is the cost of the water, Et is evapotranspiration, Es is soil evaporation, UCC is the uniformity coefficient of Christensen, pH is the price of the product, and Yx is the maximum yield. In this example, we have a uniformity coefficient Christensen of 0.75. We have assumed a cost of water of 0.1 euro per cubic meter, and the price of the product of the sorghum grain is 0.3 euro per kilogram. The maximum yield we have already discussed, that is 9 tons per hectare, 9,000 kilograms per hectare. Well, using this equation, we would come up with a result like this, 0.71. This means that the amount of water to be applied, instead of being an average of 61 millimeters, should be 61 divided by this value. It means that it should be clearly higher than 61. Then, if we go back to CropWatt and simulate for these optimum amounts that we call apparent application efficiency of 0.71, the amount of irrigation, instead of being 305 as an average, would raise to 428. So in the different locations of the field, we will have 255, from 255 to 600. Applying those amounts of irrigation, we could produce a yield from 7.6, and in the other places of the field we would achieve 9 tons per hectare. Look at this. The average yield now would be 8.74. The optimum does not necessarily mean producing 9 tons per hectare in the whole field. Why? Because to produce 9.9 tons per hectare in the whole field, we should apply the minimum of 61 in the worst parts of the field. And that would mean that the total amount of irrigation should be increased quite a lot. Therefore, this solution is better than applying just the average, because applying just the average would mean that around half of the field would be under-irrigated, and that would have a large penalty on yield. Using the equation that we have seen before, we can calculate an optimum value to optimize the economics of irrigation.